Good morning or good afternoon, depending on where you are. My name is Professor Orata. We are continuing with our thermodynamics lectures. Today we look at compressors and reciprocating expanders. And reciprocating expanders. Now, when we talk of a compressor, think of it simply as being that equipment or machine which takes that fluid from a low pressure region, compresses it, and delivers it to a high pressure region. So that a compressor basically, if you look at the commercial ones, a compressor basically, in terms of just a schematic of its configuration, you just have some piston unit, you have some magnetic components there, the coil, could have a stator, then you could have dampers and so forth. There's a piston, so here you are able to suck in, and here to discharge. That, of course, is a piston. Now, this compressor, you can have a positive displacement compressor where, for example, there is a solid boundary. There's a solid boundary which stops the backflow, of fluid as a result of those pressure differences. So that's a positive displacement compressor. And those are examples of reciprocating machines. There's a positive displacement compressor. A air compressor. And a steam engine. All these are reciprocating equipment. Now, on the other hand, a turbo expander does the reverse of what the compressor does. You'll fill in steam, a highly pressurized steam, as you have seen in the Rankine cycle, and then of course it will expand it, doing work in the surroundings. So our main focus will be on the work by these reciprocating expanders. Now, in terms of the schematic, there's a schematic of a turbo expander, so that you have a feel of what it is, a schematic of a turbo expander. You can think of having in these units, having here in these particular units, you have a shaft, compressor, then you can say here we have a condenser, and of course here we have an evaporator. Here you have liquid, you get liquid plus vapor, of course cold. In the evaporator here, you take in some heat, so that when this comes out, you'll have warm air, warm vapor. On the compressor, it will be hot vapor. And of course, the condenser will lose some of the heat. So let's say plus, minus heat, Q is heat, remember? That's just a schematic of a turbo expander. Now let us look at what happens with these reciprocating expanders. And the best example which you want to use is the piston. cylinder model. Remember, we talked about the piston cylinder models in our earlier lectures when we were talking about computation of pressure volume work, whether reversible or irreversible, and when we were developing expressions for adiabatic reversible work. And of course, if you look at that expression also for polytropic processes, those equations are basically just in the same box. They're all in the same box. So again, here we will use a piston cylinder model. Now, remember when we did the pressure volume work in those derivations, we made assumptions about the piston, which are now not true here. One, we had assumed that the piston, for example, for totally ideal situations, these are not very ideal situations because they're actual practical realities. Now, if you assume ideality, you would assume the piston is massless, frictionless, perfectly fitting, and rigid. And those were assumptions which you made then. Now, in the same way, here now we have our piston cylinder models. This is the piston. This is the piston, and this is the cylinder. We have what we call the clearance volume. We're going to talk about it. What we call the clearance volume. I need that space, and I might need to use the other side. Let's say clearance volume. And here we have the top dead center, TDC. Down here, you have the bottom dead center, VDC. Now, this piston, I've marked it here, I've marked this deliberately. They normally have rings. And these rings, one normally deals with compression, and another one deals with oil. So these are rings normally, which are common of this piston. And of course, there is a connecting rod. There's a connecting rod. There's a connecting rod. Of course, the motion will be reciprocating. Remember, this is connected to the shaft. Normally call it crankshaft. It's connected to the shaft. And I want you to note that in here where we have this connection to the shaft, there's normally bearings. They're normally bearings. Normally they're called cone bearings. They're cone and rod bearings. These are normally called cone bearings. And as we have always said, and of course, there are channels which allow oil to flow through them so that there's no excessive friction. So remember, the bearing facilitates rotary motion. Very important for us to know. And of course, this is a rotary motion. So basically, this is the cylinder. So we are there. Now, we have the valve. We have the inlet valve. We have the spark plug. And of course, we have the exhaust valve. Now, if you look at that process, the piston cylinder model, it can expand, it can expand, or it can compress the system. It can expand, compression, expand, compression. Of course, compression will involve expansion, and compression will involve changes in the volume, in the actual volume. But the volume which is swept we talk of the swept volume. We normally talk of the swept volume. Let me illustrate it in a simple manner. If we have a conventional, very simple pressure volume work unit for the cylinder where we have the piston, where we have the piston and we have the cylinder. We have the piston and we have the cylinder. Now, in this particular case, if you have an external pressure greater than the internal pressure of the gas, then you will push the piston down. That's a compression process. And if the internal pressure, that is compression, if external pressure is greater than internal pressure, but we'll have expansion if internal pressure is greater than external pressure. And so when you have that change, let us say these changes are involving these 2 points, that is level 1 and level 2. This is the volume swept. That is the volume swept volume. Now, what is the pressure volume profile? That's the indicator diagram for this particular process. What is the indicator diagram for this particular process? An indicator diagram is a plot where we are plotting the cylinder pressure. Now we plot the cylinder pressure versus the cylinder volume. Cylinder pressure versus the cylinder volume. And remember, this is an indicator diagram, and it's a graphical representation of the total work done in that particular system, because if you take pressure volume, pressure is force over area. Remember, volume is area times some displacement. So if area cancels with that, you have force times displacement, that will give you work. So the area under those plots are normally representative of work. So the kind of profile you get for that rotatory reciprocating expander, we will get so we can have state point 1, let's have that state point 1, then have state point 2, state point 3, state point 4, state point 5, and 6. Now, state point 1, that's the state points. Of course, these are positions which are defined by thermodynamic functions. The state defining the state of that particular system. Now, at state point 1, we'll have the inlet, valve open. And when it's open, fluid will be put in the system. Because this is an open system, so you put in the fluid, it will of course expand and do, of course, expansion, doing work in the surroundings. Just like the steam engine, you know, it gets the steam at very high pressure gets into the turbine, and of course the turbine does work. That we have seen when we are dealing with the Rankine cycle, in our lectures on Rankine cycle, and also in our lectures on steam turbines. We have talked about that high pressurized steam from the boiler into the turbine. Of course, this expansion work is done, and of course the process moves on. So I advise you, it's my humble request that you go look at those discussions there, so that you get your bearing completely right. So we have the inlet valve open, so the fluid put in the system, let's call that fluid letter MF. And of course there's additional fluid which is put into the system to take care of the clearance volume. Why do we talk about the clearance volume? We talk about the clearance volume. Remember, this piston moves up, is in a block, and we have a cylinder head. So if there's no clearance, the piston will hit the cylinder head, and that will cause a lot of damage. There's also valve clearance, which must be factored in. We are going to see those as we move on. as we move on. Now, so there's additional liquid, let's call it the one which will be put in the clearance, that will be in the clearance volume, because we'll trace their behavior in the system. Now, at state point two, we have our top dead center. And at state point 3, we have the intake valve closed. Then the huge process starts taking place. That is, between 3 and 4, we have the adiabatic expansion. So 3 to 4, you have a adiabatic expansion. And remember, we are assuming that this system is reversible and obeys the polytropic process equation, which we did in our discussions on polytropic processes, where we say that PVN is equal to a constant. This was true for polytropic processes. So it obeys that. We'll have a adiabatic expansion here between 3 and 4. Between 3 and 4, we will have a adiabatic expansion. And of course, we'll have opening of the exhaust valve. What happens at that point? At that point, we offload this liquid delta MF, not delta MC for the clearance volume, delta MF. The one of the clearance volume is there. It's just following the rhythm of the compression, expansion, compression, expansion. It does no work on the surroundings, and the surrounding does no work on it. And so it's just there, involved in the rigors of the mechanics which is happening in terms of compression and expansion. But when we open the exhaust valve, some of this liquid delta MF exits. Delta MC doesn't exit the system. So what are we saying? So we are saying that you can actually graphically represent like you have P and V, and you have this system. So we have where we have delta MF plus delta MC, and then after the exhaust, now of course opening of exhaust, and then 5 we have the bottom dead center, and then of course at 6 we have the close exhaust valve. So we are saying that the MC does not exit the system, so again it does move back up. That's very, very important for us to know. So in this reciprocating expanders, we have seen the pattern in which work is done, and so in the next discussions we are going to actually do calculations in terms of the work done with this reciprocating expanders, work done in this particular system. So we have gotten the gist of the matter. 1, compressor. Simple way, just think of it as an equipment which has taken this liquid from low pressure, compresses it, and delivers it to high pressure region. That's very important for us to note. And we have talked of positive displacement compressors, where we have said there's a little bit of modification. There's a solid boundary which stop backflow, irrespective of the pressure gradients. And then we have talked about these reciprocating expanders. And we have said the steam engines are a very good example where you feed in the pressure, the steam at high pressure, and then of course, out of the expansions, you're able to do work, and then of course others, go to the condenser where they are cooled, and the process moves on the basis of Rankine cycle and the interface Rankine Carnot cycles and so forth. So very important for us to know. And we have seen new terms. We have talked about clearance volume. That volume is very important so that we don't have the piston and the cylinder head coming together, hitting them. The piston hitting the cylinder head. That would be a problem. If it hits, it can crack the piston. Can crack the piston. And also your valve clearance has also to be done so that all this does not happen. And by the way, valves are very important, especially in internal combustion engine, because if they are not timed properly, then the firing system will fail, and then the pistons will be moving in all manner of ways, and can lead to very massive destruction of the unit. Now, and then we have said that this system, we are assuming they are reversible. And another important assumption is that let's just sketch something here. Just deal with the top. Let's deal with the top of our system. We say that we have the inlet valve, we have the plug, spark plug, and we have the exhaust valve. Now, it is very important, that the substance here in the inlet, entering at the inlet and at the exhaust valve, the substance remains the same, unchanged. Very important. Number two, we are assuming, like you have said, that this system is reversible and obeys the equation of state or characteristic equation for polytropic processes, PVN is equals to a constant. And finally, we are assuming that the velocity M of the fluid flowing the system is very small, negligible. So kinetic energy is not an issue. So kinetic energy can be ignored. So let's stop at that particular point. We'll pick up with other thermodynamic lectures.